Hello and welcome. In this video, we're going to look at how to calculate parallel RLC circuit impedance. Parallel RLC circuit impedance is a little bit trickier than series impedance, and that's because we have to use our susceptance, admittance, and conductance for the circuit instead of our resistive loads. And so that means that we need to start off with our admittance equation, which is our Y value. We can say that Y is equal to our conductance for our resistor minus J. These are going to be our imaginary numbers, our capacitor and our inductor. Inductor always goes first with this one, so we'll say that our susceptance of our inductor, we call that BL, minus the susceptance of our capacitor, BC. Remember that conductance, admittance, susceptance, those are just the opposites of our resistor value. They're the reciprocal of our resistors. So in this case, our conductance, our G variable, is equal to 1 over R. So we can solve for that. We can say that we have 1 over 270. And that can be our susceptance, or conductance for our resistor value. So 1 over 270. That gives us a millisiemens value. And so right now it's in Siemens, so we'll move that decimal point over and say that it's 3.7 millisiemens. So that gives us our G variable. We also need to find our BL and BC. Those are the same equation, just for our inductor and our capacitor. Just keep in mind that they need to use XL and XC. They need to have the resistance values for those. So BL is equal to 1 over XL. So we don't have XL, we need to find XL first. So we'll say that our XL equation, so XL is equal to, that's our 2 pi FL, so our frequency is 13,000, multiplied by our inductor value of 33 millihenries, and so we'll move that decimal point over, 0.033 henries, and we'll plug that in. So 2 pi times 13,000 for our frequency, multiplied by 0.033. That's our henries value. We'll set that here. And this is our resistance for our inductor. So the inductive reactance, 2,695 ohms. And we want to convert that over into susceptance. So we'll use that 1 over XL, and that will give us our susceptance value. Send this out and say 1 over 2,695. And that gives us a pretty small number. We'll say that our BL is equal to 1 over our XL, and that is our 0.371 millisiemens. Really small. Next, we have our BC that we need to find. BC is equal to 1 over XC, right? Capacitive reactance. Our XC is equal to 1 over 2 pi. Frequency, 13,000. Multiplied by our capacitor. Capacitor is real small here, 0.03 times 10 to the negative 6. We'll plug all that in as is there to find that value. We'll get an ohmic value out of this for our capacitor. Send this out, we'll say it's 1 over 2 pi times our frequency, 13,000, times our capacitor value of 0.03 times 10 to the micro, which is negative 6. And that is our answer there. So we have 408 ohms. So our inductive load is much larger than our capacitive load at this frequency here. And we'll say that our BC is equal to 1 over our 408 number. We'll plug that in. 1 divided by 408 gives us a really small susceptance value. That's what we wanted. So we'll move that decimal point over and we'll say that it's 2.45 millisiemens. All right, so now that we have all of our variable numbers, we can plug in. We can say that our Y value, our admittance, is equal to G. We know what that is. That's 3.7 millisiemens minus J, BL minus BC. We've got to keep those in the right order there because we're going to have a negative that pops up that we need to actually work with. 0.371 millisiemens minus 2.45 millisiemens, right? So when we subtract these two, the second number is going to be a little bit larger, which means it's going to pop out negative, and then those two negatives are going to cancel each other, and that's something that makes these answers wrong all the time. So just watch out for your negatives. 0.371, they're both in milli, so we can just subtract them directly. 2.45. That gives us that double negative, and so we'll say that our final admittance value, Y, is equal to 3.7 millisiemens plus J, so that negative on that J up here, and the negative for this one is going to cancel each other out. And so we'll have a positive there, and we'll say that it's 2.079. We can round that up to 2.08. All right, and that's in millisiemens also. So this is our rectangular form of our admittance for this full circuit. We've incorporated each one of our variables, and we can just plug in from here. So we know that we want to get to our Z value, and our Z value is the opposite of our admittance here. So Z is equal to 1 over Y. So we need this to be in rectangular form so that we can invert it over. So that's our next step, is to convert Y into rectangular form so that we can take the reciprocal of it. So rectangular form is that square root equation. So we'll say that our Y is also equal to the square root of our A squared plus B squared, A being 3.7 millisiemens squared, plus B, which is the 2.08 millisiemens, 2.08 millisiemens squared. I like to plug these millis in for this variable value just in case I mess up on the decimal point. So square root of, these are in millisiemens, so I'm going to move that decimal out, 0.0037 squared, plus, move this decimal out to 0.00208 squared. Is this small little number? That's what we expected. So we'll say that our Y, admittance in polar form, is equal to 4.24 millisiemens. We need to find the angle of, and so we'll get that's our inverse tangent equation. We'll say inverse tangent of our B over A. So our B is 2.08. Divided by our B of 3.7. So 29.3. 29.3 degrees. Okay, so that gets us rectangular form. We just need to invert this one more time. So we'll say that we have our Z variable is equal to 1 over Y. So 1 over our main digit, our rectangular angle, our polar angle is not going to change. So we just need to put that 4.24 millisiemens on bottom here, and then we'll get our Z variable out. Z equals, in polar form, 1 over 0.00424. That's at 235.8. Watch out for your notation for these ones. Really, really going to get you. 236 at an angle of 29.3 degrees. Keep in mind when you take the inverse of something like this, you'll also flip your positive to a negative. And so in this case, the 29.3 will be a negative 29.3. That will stop you from getting your answers correct, so watch out for those. So this is our ohmic value. This is our Z total for this equation. So we'll type that in up here. We'll say that we've got 236 at an angle of negative 29.3. After that, we need to convert this over to rectangular form. And so we'll do one more step here where we convert this z value to rectangular. That is our cosine and sine equation. So we'll say that the resistive side, which is this first number here, is equal to the cosine equation. So 2, 3, 6 cosine of negative 29.3 degrees. And then our x total, which is the second side, our j side, is equal to 236 sine of negative 29.3 degrees. We'll plug those in here. Say that we have 236 cosine of negative 29.3, 205.8. We'll go 206 on that one, so 206, that's our ohmic value. And we'll send that out. Say that we got the same thing, so 236, but sine of negative 29.3, negative 115. 115, that's also an ohmic value, but it's for the imaginary numbers, our inductor and our capacitor. 206 and negative 115. Watch out for your negatives on these. So I'm going to hit go on this and check it. That's our answer there. Erase a couple of these things here. So just keep in mind that those negatives will transfer back and forth, and you want to keep very close eye on where those happen. So if you take the reciprocal of the base number, like we did for our y here, make sure you make that angle that came with the y a negative after that, right? And then use that in your polar and rectangular form conversions as well to keep track of that negative. Right? Let us know if you have any questions.